Hello, everyone. This is the DigiQ Journal Club session 4, and today we are going to discuss quantum statistical inference. A bit of introduction of myself. I am Amey Bhatuse. I am a master student in quantum science and technology here at University of Barcelona. And without further ado, let's start the presentation. Okay, so let's start with the motivation, like why this talk, why quantum statistical inference. So the main motivation is to address a foundational gap in the world of quantum mechanics or quantum computing is that quantum mechanics provides us the laws of physics, like the most basic laws at the smallest level. Like we have the state, we have Hamiltonians, we have unitaries, and all this math that we do. But when we run experiments to validate this theory, we only have raw data, which are like counts or clicks or currents. So QSI is like a mathematical bridge between these two things, theory and experiment. And through this, we are trying to like answer a fundamental question. Let's, given the laws of physics, like what is the maximum amount of information can we extract from a quantum system? That is basically like asking from your experimental data, how much can we understand about the underlying quantum system? And so QSI sits at the intersection of like three major pillars in the whole quantum landscape. But the first one is quantum computing, where we have the verification or benchmarking of quantum gates or quantum processes. And all of this comes under a technique called tomography, which we will see as we go further ahead in the presentation. Then there is the second pillar is quantum communication, where we have this whole pipeline of transmitters, receivers, repeaters, and we want to send like a photon from one point to another without any kind of attenuation and all those things. And there we have another use of QSI where we want to distinguish between two signals or two or more signals uh, and in a noisy channel. Let's say if the channel was noisy in those kind of situations. And then there's another pillar, which is quantum sensing, where we are asking the question like, what is the ultimate precision can we reach in measuring a parameter for an experiment? So this is the whole where QSI sits in the whole quantum landscape. So let's move ahead. And so this is the roadmap that we are going to take today in this seminar. There are four topics: uh, quantum hypothesis testing, asymptotic hypothesis testing, quantum parameter estimation, and quantum state tomography. Now, before we go ahead, uh, I want to caution you that QSI is like a mathy topic, and there are always like a lot of proofs because it involves advanced statistics, and it's less of physics and more of math. But because it's an introductory talk, I've tried to like keep it very simple and surface level, I can say. I'm just going to give you the intuition behind the math. I'm not going to go deep into the math because, of course, we don't have time, and also it's introductory talk. So there might be some like inaccuracies in my presentation, and so I'm happy if you can just point them out or maybe give feedback at the end. So let's start with the first topic, which is quantum hypothesis testing. And the basic question that we are trying to answer is, how can we find the physical limit of answering this question? Which state is this? And now I will make it more clear now. So quantum hypothesis testing is basically like a discrimination game where your setup is like you have a black box source which emits a quantum system, let's say a photon or an electron, something like that. And you have certain knowledge about that source. We know that it gives us a particular set of states that we know, and it also gives us the frequency of that frequency of occurrence of that state. That means with how much probability that we are going to get each of these states in that set. And what we can do in this protocol is we can perform a single measurement, and then we have to, based on the outcome of that measurement, we have to decide which state was sent. Now, there's a fundamental challenge in this. In classical physics, we can always distinguish distributions if we have enough resolution. But like if you check in classical distributions, you have either one outcome or another outcome. And the measurement is very clear. You do one measurement or the other measurement. But as you know, in quantum physics, your quantum state is actually a superposition of all of those outcomes. And the overlap is not either 0 or 1. And that creates like a very hard limit on your certainty. So let's see how we can translate this problem in probabilities. And then we go on to answer this question, like how do we do this thing in quantum physics? Let's check the classical part first. So we have like a classical binary test where we have two hypotheses, H1 and H0 and H1, and let with the prior probability with P0 and P1. And so it's very easy to see like there can be two types of errors. Like you, based on your measurement and the outcome that you see, you said, okay, it was the hypothesis H1, but maybe it was actually H0. So you actually gave a false alarm. And there can be another type of error where it was actually H1, but you said, okay, it is H0, which is the zero hypothesis, null hypothesis. And so it was a miss. And we named these errors as type 1 and type 2. And so the average error can be eta 0 alpha plus eta 1 beta. And so in classically, if you look at it, you can simply look at which probability density was higher and then say, okay, for this outcome, the probability was higher. So that's it, you have it. But as we saw, in the quantum version, it's harder because this at a given point itself, it changes depending on what basis you're measuring. And because you change your choice of measurement and everything changes. So to fix this, let's start with like a mathematical description of measurement itself. So we are diving into this something called POVMs, which is the positive operator valued measure. It is a set of operators, which are matrices basically, representing our possible guesses, which satisfy this condition that all summation of all these operators should be identity. And in to give you just give you an intuition, it basically means that we must always provide a guess. There should be no operator that's like it's not providing any answer to us. And so the probability that how do we get the probability of our answers, like which answer that we have? So that is given by like let's say you have guessed I, but the state was J, is given by the bond rule, which is like the trace of the density matrix, the state, into the operator. And the total probability of success will be eta I, which is the prior probability into the trace, and you just sum it up. Now, we know, okay, this is the formula, and we know the state, we know the eta, but what we don't know is the measurement operator. So our goal is to find a set that can align best with these quantum states, with the set of quantum states that you have. Okay, so let's start with the simplest case. Let's say we only have two states. So here comes our first bound that we are going to show in this presentation, which is the Hellstrom bound. Let's say you have two states, rho 0, rho 1. Now, the ultimate success of probability that you can get is given by this equation. I haven't mentioned the proof here, but just believe me that it is this. And to explain this a bit more, this quantity is essentially the trace norm, which basically measures the total distance between the operators. And in the special case where you have like equal priors, that the states have equal frequency, 0.5, then if the states are orthogonal, then you can perfectly guess. And it makes sense. If the states are orthogonal, then you can always have a measurement that can show us which state it was, because it will give different outcomes for the both states. And if the states are identical, this also makes sense that it's going to be completely random. We have to purely guess based on the outcomes, like what state it was. And the physical intuition for the trace distance can also be like, it is essentially a geometric visibility. That means, let's say you are in the Hilbert space and you're standing at the position of one state, then how much can you see the other state from that position? That's like the very basic intuition behind the trace distance that we have used here. Okay, now, so we saw all of this, like how can we get the measurement and everything, but like how do we actually build the measurement that achieves this bounds, like this formula that we have. This is done by the Oliver-Elstrom operator, which is essentially, this thing is essentially, if you see, is inside this. So the strategy is we perform the spectral decomposition, and if the eigenvalue of this decomposition is positive, it belongs to the outcome belonging to operator M1, and if it's negative, it belongs to M0. Very easy. So the insight behind this is like we are essentially slicing the Hilbert space along the axis where the states differ the most. And so we want to find M0 and M1 where these two states will differ the most. That's all the intuition is. Okay, so we saw for two states how it works. But what if you have, because at first when we saw, the problem statement was about n states. Let's check this case now. Now, this is a bit disappointing because there is no simple formula, analytical formula like Elmstrom. Instead, we have certain conditions that the measurement set can satisfy, with which you can tell, okay, you are this close to having a perfect measurement. And these are the conditions that you have. POVM is optimal if and only if this operator that we created satisfies these two conditions. First one is that it should be a mission, and the second is like this operator should be greater than this quantity, the priors into the quantum states for every quantum state. So, and why this is useful is like, let's say you don't find the perfect measurement, but these conditions at least let you know how close you are, how your current guess, how good it is. And so it's like a test for perfection. Now, since finding the exact measurement set is hard, can we find a good enough one in special cases? Because that, as we saw, like in general cases, we don't have like a simple formula. Maybe in special cases, we can do something. So here comes the PGN, which is the pretty good measurement. Now, this is a very practical and operational explicit construction, which is done for very specific states. And it's basically like you create a measurement set with this kind of construction. You have the prior probability, you have the quantum state, and you are adding these extra operators here, where this row is actually the summation of the prior into the quantum states. Now, an insight here can also be like these operators are actually the normalized versions of each prior into its quantum state. I mean, if you see, this is like minus half and plus minus half. So if both of them are like in denominators, and so it's like theta I, rho I divided by rho. I mean, it's not exactly like that because these are matrices, but if you want the intuition, the intuition is this, like you're basically normalizing each of these quantities by dividing by its sum. So now, just like I said, this is state dependent because your measurement adjusts itself depending on the ensemble, because you can literally see like the measurement operator is depending on your set of quantum states itself. And so it is only optimal for symmetric set of states. Now, I haven't mentioned anything why exactly this is possible, because there are a certain other set of conditions that it needs to satisfy. But yeah, so, and the scaling is also guaranteed to be close to the true optimal success probability that you can have. That's why this is like a more operational construction that is used in experiments. And so now let's see for pure states, how can we do this? Because like usually symmetric set of states, with pure states, we can easily check if it's symmetric or not. So, and actually this does transform into a very elegant formation where, let's say you have pure states, then we can define a matrix where each of your elements, ij, are the square root of the multiplication of the priors and the overlap between your quantum states I and j. And your success probability is essentially the square root of each I squared. Like basically the diagonal elements squared and the summation. And why do you want to use this? Is because instead of working with large density matrices where you have 2 raised to n by 2 raised to n elements to deal with, we can actually work with like a smaller matrix where it's only n by n, where you have n states. And so the gram matrix captures all the relative overlaps in just one object, and you get the success probability by just checking the diagonal of that gram matrix. So now that we are here, we have seen like so many techniques yet, like, but still, I mean, all of these methods allow for mistakes because that's what we saw in the beginning. We are checking success probabilities, but there's also type 1 and type 2 error. But now, what if we refuse to be wrong? We don't want any errors. So this is another technique that we have, which is called unambiguous state discrimination. And this is used in specific cases, specific experimental cases, where you can't afford to do any mistakes. So the rules are very basic, like we only get 0 or 1 if we are very 100% sure. And let's say we are not sure, then we have this another operator in the measurement set, which gives us an evidence that the solution is like inconclusive. The outcome is inconclusive to decide which state it was. And the constraint mathematically can be put like this, where you cannot have errors, which is like this is the type 1 error, type 2 error, and no false alarms and misses. So for pure states, this if we check C is the overlap between the states, then the failure probability is always going to be more than at least this overlap. So we can see, I mean, if you're trying to not get errors, then we have to be ready to deal with like higher failure probability. And for states with overlap C, we must accept a failure rate which is more than at least C, which is the overlap between states. Uh, so far we have seen how to distinguish states in a single shot. Now let's check some numerical tools. How do we do it? Because not every time that you have a problem that you will have an analytical solution, which as we saw, like for the Hellstrom bound, we have an analytical formula, but as we go to n states, we don't really have an analytical formula. And so in this kind of situations, we use some other techniques from mathematics. We treat it as a convex optimization problem. So we want to find this, as we saw, this is the whole goal that maximizes a success. So the success probability is this, which is the one that we saw earlier, and subject to this kind of constraints where every operator is positive semi-definite. And this condition was also what we saw before. We should always provide a guess. Now, why are we using this? Why HDPs? So the thing is like semi-definite programming is essentially built for these kind of problems where your variables are actually positive semi-definite. And also there's been a lot of literature on solving HDPs using interior point methods or iterative algorithms. But basically there's a lot of literature on these kind of things. So now there's another question, like how do we know if we solve these equations, this semi-definite program, how do we know that we actually reach the optimal success probability? We have the actual optimal measurement. So in optimization theory, there's for every maximization problem, there's a minimization partner, which is called as the dual. And in this problem, what we are going to look at is like we want can tell us about that basically can tell us about every state. So we want to minimize this y such that y is greater than rho I, which is basically the multiplication of your prior into the quantum state. And so here, as I said, like y actually has all the quantum states beneath it. So for a valid y, your success probability can be less than this, the trace of y. So the dual is like an upper bound, a ceiling on what physics can allow. And in the case of strong duality, where you actually find that your success probability is equal to y, and so you can think of y as like a witness that accounts for the total information available in the ensemble, which I said before. It has information about every quantum state in your set. Okay, so yeah, when the guessing meets the ceiling, we find the optimal solution. Okay, so this was the summary of part one, which is quantum hypothesis testing. We checked the binary case where we have the Helmstrom bound, which gives us like a geometric distance between the states. Then we checked the multi-state case, and in that we checked like a very special case of pretty good measurements and Gram matrices and how it provides not exact but maybe near optimal practical answers. Then we checked the case where we cannot afford to be wrong, which is unambiguous state discrimination, but it at least lets us be certain that the outcome that we have is correct. And then we also checked some numerical tools which we can use in case we don't have any analytical answers. So we have seen the discrete problem for one copy. Now, what if we can have multiple copies? And here comes our section two, which is asymptotic hypothesis testing. And so here's the setting. If you go in laboratory settings, I'm sure there are some people who are working here in this meeting who are working in laboratories on experimental stuff. And like we rarely have just one copy of the state. What we have is like an ensemble of n independent and identically distributed copies. And mathematically, you can write it like this, like as a tensor product. So the question that we are asking is like, what if we increase this n copies? Can we do better than what we saw? The success probability that we had, can we do better? And somehow the answer is yes. As n increases, so even with states that have very high overlap, which must be very difficult to distinguish, actually become distinguishable. And the error probability vanishes exponentially with this number of copies. Now, okay, this seems good, but like when we want to find how much, and this is the objective of asymptotic hypothesis testing, where you want to find the error exponent, which is the rate at which your distinguishability appears with respect to the number of copies. So if BE is like an exponent of minus NR, the constant N is the number of copies. The constant R tells us how much distinguishability each extra copy provides. Now, once again, here's a caveat. We just saw there's not just one error. We have two types of error. That's type 1 and there's type 2. And so there are two ways to be wrong. And which error are we exactly talking about when we say that we're going to check the distinguishability? So before we move on, let's check how we can deal with these two errors. So we want to minimize one error while capping the other. So basically, if we can just check one error and keep the other error aside, how we can do it. So to minimize the type 2 error, given a fixed measurement, a fixed maximum type 1 error, there's a optimal P of M, which is a projector onto the positive part, which is the positive eigenvalue part of this operator that I've mentioned. Lambda is the Lagrangian multiplier chosen to satisfy this condition. And this is the quantum Neyman Pearson lemma. Now, this is all mathematics, but the insight I can give from here is like, this is the general Helmstrom measurement that we can have. And what it tells us is like, even with the best measurement, even with the constraints, the best measurement that we can have is actually a binary partition in your Hilbert space. And this is actually very insightful because it helps us create better exponents where we don't need to consider that we are only having one error and we are capping another error. So what happens to this constrained error as we add more and more copies? Here you can, like, just like I said, we don't want to just have one error in consideration and focus and just discard the other. But then there comes a question like, then which one do you check? So there can be two cases. One is asymmetric, where there is asymmetric case where you're focusing more on one and you can be fine with the other to be not as accurate as possible. So there's the type 1 error where you mistake rho for sigma, and we fix this to be very small, and we are fine with this error basically. But we want to make sure that our type 2 error should be as minimum as possible. And if you write mathematically, this is the minimization of this, we have sigma with the measurement operator, and these are our n copies. And here, our type 1 error should be it should be less than epsilon. And so the intuition behind this construction is like, if I promise to almost never misidentify rho, how easily or how fast can I correctly identify sigma? That's the question that we are trying to answer. And so the answer to this question is a very important result, which is the quantum Stein's lemma. And the theorem says that if we have infinite copies, then this type 2 error that we have, this beta, actually follows this relation, which is the exponent of minus n and this quantity d bracket rho and sigma, which is actually called as the quantum relative entropy. And I will explain what relative entropy is, but there's also a caveat here that this rate, if you see, it doesn't depend on our epsilon. So you can always have like whatever kind of epsilon, like maybe 0.1 or 0.2, and the ultimate scaling is still dependent on what your states are. And it's actually very interesting because we assume that maybe if we change the epsilon, then our type 2 error should also change. But fortunately, it doesn't. The math shows that it doesn't. Okay. So we have the exponent now, which is the relative entropy given by the Stein's lemma. But what does it represent physically? So relative entropy is like a statistical distance between quantum states. It tells us like how much information can we have about a quantum state if we already have like a different quantum state. And so there are a few caveats here that it's not symmetric, because if you just change the positions of rho and sigma, you can see it's not symmetric with just basic algebra. So it matters like which state did you assume as your null hypothesis, which is the H0 or the first state that you assume to be there. And so here, if the states are identical, also the relative entropy is going to be zero. So the more different the states are, the larger D is, and of course, for the faster the error drops. Of course, you can't assume that even in n copies, that if the states are identical, even in n copies, they're going to be still identical. Only if they have like some kind of distance between them, then we can assume, okay, we can have n copies and then we can distinguish it. Okay, so we check the asymmetric case where we are fine with one error, but we want to minimize the other. Now, what if we care about both the errors and we want to minimize both the errors? Here comes the symmetric case. If we have no reason to favor alpha or beta, we minimize the total error, the average of them. So let's go back to the Hellstrom measurement that we had. For n copies, the bound is given by this, which is, if you see, the formula is exactly the same. We just replace the rho and sigma with the n copies that they had. And as n tends to infinity, these two become orthogonal, which we said before. So the success probability goes to 1 and the error goes to 0. Now, this looks good on paper, but like, how do you know, like at what rate? Because that was the whole point of this section. Like, we want to know the exact a scaling of how much copies do we require such that these become orthogonal. And so the rate, so the question is, does it decay at the same rate as the asymmetric case, the Stein's lemma? And the answer is no. The rate for this decay is actually much harder to compute, and it is given by the quantum Chernoff bound, which so the average error vanishes at this kind of rate. I know it doesn't look very good, but and so there's a bit of a plug here. Actually, if there's people in the meeting from Barcelona, this bound was actually done by this like they gave people from Barcelona. So people from MICFO and UAB, they came up with this bound. I think it was in 2006. And it's a very seminal result in the field because no one knew how to solve this symmetric case. And they came up with this bound. Okay, so let's come back. Uh, there's this term inside that we have the trace of rho sigma, and have exponentiated to s and 1 minus s. And just to give you like a basic intuition, this is the overlap between these two states decided by this extra constant that we have, s. So we want to find the s such that this overlap is minimized. And so basically the s is the constant that balances the two errors, type 1 and type 2 errors. So why do we need this s, and why is this math so difficult? So classically, if we had, rather than quantum states, let's say we had probability P1 and Q1, Qi, then it would have been and so the calculating these two quantities is diagonalizing these matrices, and also like how they have this kind of special case, but they're not always uh, okay. So the physical meaning behind this whole construction is like non-commutativity reflects that the two states of course don't have similar eigenbasis, eigenorientation, which actually makes it harder to find like a single measurement basis that distinguish them perfectly, which we saw earlier, like with the quantum Neyman-Person's lemma, which said that whenever you're trying to distinguish any kind of between two states, it's basically like you're trying to find a slice, a perfect slice that can where in one slice you have one state and the other slice you have other state. But this non-commutativity of quantum operators, quantum density matrices, is difficult to do. Okay, so far we were trying to distinguish states, but let's go further ahead and ask another question. What if we want to distinguish the process, the quantum source that created these states? So here comes the section on channel discrimination. So in many experiments, we actually don't start with the state. We actually have like a source or like a channel that can produce that state. Let's say a noisy fiber optic cable. So in this scenario, we want to check like which channel it was, whether it was this one or this one. And so with the basic protocol that you can use, like we can have like an input state, we send it through each of these channels and then measure the output. And if it was one output, we say, okay, it was this channel, the other output, the other channel. Now, here, actually, we can do something much more. We are not restricted to sending simple states because we have a property in quantum mechanics called entanglement. And maybe we can use this to distinguish between these channels in a much more efficient way. So let's see how entanglement can be used. So instead of sending just one state, we can prepare an entangled pair between a system and a reference, and then we apply this channel, and then we check, okay, how much both of the outcomes are different. So this channel might, and the idea is like maybe this channel changes the correlations between A and R, even if it like maybe doesn't change the quantum state itself that much, and maybe that helps us. So this makes the two channel look more different than a simple measurement on just the quantum state. Okay, so this is a good intuition, but like how do we quantify this? This can be done using the diamond norm, which is this formula where you have one channel on the system and the reference, and another channel on the system and the reference, and you want to find the maximum difference between them given a particular state and reference. So the one way of looking at it is like it is a trace distance for channels, and adding an well, another thing of using the specific construction is like adding an extra disconnector system doesn't change the value, and also computing this quantity can be framed as a semi-definite program. That's the reason that we use this diamond norm. Okay, now let's go a step ahead. We saw that the diamond norm assumes a parallel strategy where you have a system and a reference. But what if we can actually use these channels in a sequence? So I have only mentioned this quantum comb here, but it's actually a very advanced concept. That's why I haven't mentioned any math. But the basic idea behind this sequential construction is like you have a mathematical object in the form of a circuit where your channels can be fit as slots in this circuit that account for memory from your like your previous outcomes, and then you can feed these outcomes back again in this circuit and to maybe to help us distinguish between the channels. And the idea is like maybe allowing for this sequential distribution can help us distinguishing between these channels. And so the strategic hierarchy between these three techniques is like if you have single shot, then you have some probability of success. If you have entanglement assisted channel discrimination, then you can have a higher chance of success. And there's another protocol that we can have, which is a sequential protocol, which is called quantum combs, where you can have much more high probability of success. So the key takeaway was like adaptive strategies can distinguish channels that are otherwise identical, which which shows us that the ultimate limits of process discrimination is not just in single shot or multi-shot, where you can actually have where you can actually use things like entanglement or something much more things in quantum mechanics to do channel discrimination. Okay, with this we are once again at the end of another section, which discussed the Neyman-Pearson's lemma, which told us that the fundamental rule for this state discrimination is essentially a slice in the Hilbert space. Then we checked there can be two cases to suppress the type 1 and type 2 errors. One was asymmetric, was based on the Stein's lemma. The error exponent was relative entropy. For the symmetric case, we had the Chernoff bound, where we showed okay, non-commutativity is actually a very big hurdle in our state discrimination task if we have multiple copies. Then we also checked, we went a step further. We checked channel discrimination, where we showed that there's a quantity called diamond norm, which can use entanglement as a resource to distinguish between these channels. Okay, so far we have seen a problem where we were already given the states, and we just wanted to distinguish whether it was one or the other. Now, let's ask a question. Like, what if we want to estimate a continuous parameter rather than a discrete choice where it's one or the other? And then we also want to ask, how precisely can we do it? So here comes the section on quantum parameter estimation. Uh, so here's the setup. We are given a, let's say, a state, rho, and it depends on unknown continuous parameter, theta, which can be any real number. And our goal is to construct an estimator based on the measurement outcomes that we can have and to identify the exact value. And so we want to make sure that this estimator matches our true value of theta. So the estimation pipeline is like this. We prepare some state, rho zero, based on theta. Then you apply the measurement, say your measurement set to get some data, and you construct the estimator. And then you want to check like how close you are. For that, you use the mean square error between the estimator and your true parameter. So how do we know that the estimator that we constructed using this protocol is actually good enough? And so we have a certain set of conditions that this estimator should satisfy. And these are the first one is unbiasedness. So on average, we assume that the estimator hits the true value. And the problem is if it's biased, then we can, in cases like the quantum churn of this QCRB, we must be adjusted by a factor like this. Then we have consistency. So as we collect more data, as n tends to infinity, the number of n is the number of samples here. Then the estimator converges in probability to the true value. And the last condition is efficiency, which is the estimator should be efficient if its variance actually reaches the Cramer-Rao bound, which we will see what the Cramer-Rao bound is now. So while many estimators are consistent, finding an efficient one is the ultimate goal. So let's start first with the classical case, where you have a classical distribution of outcomes which depend on a certain parameter, and how well can we estimate theta. And so there's a quantity in classical statistics which gives us this answer. Spatial information, which measures the sensitivity of your outcomes with respect to your parameter. So it basically asks the question like, how much can the distribution of your outcomes change if we change the parameter by a certain amount? And you can quantify using that with facial information. Now, how far can you go? How much precision can you have? That is given by the Cramer-Rao bound, which sets the precision limit. VAR is the variance of this estimator is greater than or equal to 1 upon the number of samples into the Fisher information. And so what is the physical intuition behind this is that your Fisher information is actually a kind of a measure of the steepness in your change of distribution with respect to the parameter. And so if the probability distribution changes very rapidly, we can estimate theta very precisely. And this is the point of Fisher information and the Cramer-Rao bound. Now, this was the classical case. In the quantum world, the distribution is actually depending on the measurement that we choose. So how do we do it in the quantum world? So in quantum sensing, the distribution is actually given by the Paul rule. And we know it's not fixed because it depends on the measurement set that you have. So here we are actually trying to maximize the Fisher information over all possible measurement sets that you can have. And this new quantity that we have, the maximized Fisher information, is actually called as the quantum Fisher information. And the basic intuition behind doing this is that we are searching for a measurement basis that can be most sensitive to the changes in your underlying state. And because that we saw, like if it's changing very rapidly, then by because of the Kramer-Rao bound, it will be very it will give us a precise estimation of the actual parameter. So now to compute this, we need to know how the state itself changes, because in classical with the classical distribution, we are sure, okay, if we change the parameter this much, then the outcome will change this much. But here, quantum state itself can be a bit enigmatic. So we want to check how exactly it changes. So where we have this operator that we use to answer this question, which is the quantum version of the classical score function. And this is the equation for that, your derivative of the state with respect to theta, which is essentially the change of your quantum state with respect to the parameter, is given by this operator, where L theta is a Hermitian operator. And what it does, it effectively points in a direction of change in the state space. And so if we measure an observable aligned with L theta, we extract maximal information about theta. Now, for pure states, this math actually can be much more simple, because pure states has some structure for the density matrix, where your L theta can be twice of this. And for the quantum Fisher information, for pure states, actually becomes the 4 times of your variance of the generator of the evolution. And the intuition is like, it is the speed at which your state vector changes if you change the parameter. And this is actually very insightful, because depending on how fast your state is changing, it can decide how precise can you measure that state. Can you measure the parameter that is creating that state? So this allows us to state the ultimate limit for quantum precision, which is the quantum Kramer-Rao bound, where for any unbiased estimator, theta, we checked the condition unbiasedness before. The variance of this estimator should be greater than equal to 1 upon n into the quantum Fisher information. And so the such optimal measurement is the one where you are measuring along the eigenbasis of L theta, because L theta is the direction in your state space that gives us the maximum rate of change with respect to the parameter. And so it gives us the most precise solution to our parameter. So if you want to measure multiple parameters, then this becomes a matrix, and the bound relies on the inverse of the matrix, because it's in the denominator, so it relies on the inverse of this matrix.
Anyway, sorry to interrupt you.
Yeah, yeah,
We're
yeah, yeah,
we're reaching close to a time limit, so just wanted to make you aware. We're about half
yeah, yeah,
12
yeah. I mean,
almost.
we just have one more section. So I mean, that is a small section. Yeah. So
Awesome.
yeah. So let's check an application where you have a parameter theta encoded by a Hamiltonian, and this is your rho theta, and these are your unitaries, and the quantum Fisher information is for this is constant and is actually related to the variance of this Hamiltonian for the probe state. And the strategy is like to sense it better. We don't just need a bigger Hamiltonian. We need a probe state that is spread out over the eigenvalues of this G. So this actually leads us to one of the most famous scaling laws in quantum physics, is that if we have n probes or n atoms of photons, if they are untangled, then you can just multiply the Fisher information, and the variance is given by this scaling, which is quadratic, 1 upon, which is the square root of n. And if you have entanglement probes, entangled probes, let's say you have a GZ state where you have n copies, then you actually get like a quadratic improvement in precision. So once again, we see like for this here, this case also, entanglement actually provides a quadratic improvement in precision. Okay, so with this, we are once again at the end of another section. We checked quantum parameter estimation. The goal was to minimize MSE for continuous parameter. We have tools like quantum Fisher information and the symmetric logarithmic derivative. We check the bound, how far can we go with this quantum Fisher information, and then we also checked the scaling, like how can resources like entanglement help us. Okay, with this we are at the last section of our presentation. It's called quantum state tomography. So in part 3, we checked how can we get this parameter that created the state. But what if every element in your density matrix was a parameter? And here, this is the question that we're trying to answer. Given n copies of an unknown state, we want to reconstruct the entire density matrix. And to do that, we use something called tomography. And the classical analogy for this can be in medical tomography, you have 2D X-rays to build a 3D body. In quantum state tomography, you have 1D probability outcomes to build a D by D density matrix. Now, to reconstruct the state, we must first count how many pieces it has. And it turns out that it's a difficult problem because the density matrix is a D-level system, and there are D squared minus 1 independent real parameters. And if we just check the scaling, if we have 1 qubit, we have 3 parameters, which are the parameters of the block vector. And if we have k qubits, the scaling is 4 raised to k minus 1. And if you see very quickly, we hit the wall, where if we have just 10 qubits, we are trying to estimate this many parameters. So how do we choose measurements to capture these parameters? So this is given by the informationally complete POVM. Any state is uniquely determined by these probabilities. And so there is a specific POVM called symmetric information POVMs or SIGPO VMs, which requires these square outcomes. And then there's another standard choice in these POVMs where you can just use the poly basis for every qubit. Now, once we have the data, how do we turn these frequencies back into a matrix? You did your measurements, you have your probabilities. How do we turn back into a matrix? Let's say if you have measured frequencies, Fi, using this Bond rule, and this technique is just linear inversion, where you just take an inverse of your transformation. Now, the issue is there's a flaw. You can have statistical noise because small fluctuations in counts can result in a unphysical estimate of your density matrix, which has negative eigenvalues. And we know, the quantum state is a positive operator. So physics does not allow states with negative probabilities, and so our estimator shouldn't either. So to fix this, we have another technique, which is maximum likelihood estimator, where if you have a state, then we look at the most likely physical state that can give us, that depending upon the measurement, that gets us close to the actual quantum state. So we maximize the log likelihood over the set of positive semi-definite matrices. And once again, this can be framed as the SDP. And one advantage of this is like the result is always physical. We can always be sure that we get a a physical density, like a physically possible density matrix, but it can be biased towards low rank states. So there's another question now. Is there a way to avoid the exponential scaling of this d square that we still have? So there is a way, which is which is called as the least square estimation, where if your MLE, my maximum likelihood estimator, is too slow, then we can treat this reconstruction as a constraint optimization problem, where you're trying to minimize the distance between this predicted and observed data. Your frequencies is the your observed data, prediction is your this quantity, and given a set of states, you're trying to minimize this, and you're trying to do it with these constraints. And as we said, we can do this as an STP, and we can add like more things where you have weighted least squares, where you can weight the terms by something like this to account for different levels of short noise. Okay, so least squares basically offers a faster solution for smaller systems like 4 to 8 qubits, and actually gives us a very similar physical estimate. Now, how do we know how close we are? For that, we have like two quantities, which is one is the fidelity, which is 1 for identical states, 0 for orthogonal, and for anything in between, it's given by this quantity. And if you have pure states, then you can just have an easier formula. Then there's also the trace distance, which as we saw earlier, so I won't go into it now. Now you have your estimate, but how do you know that it is actually correct? Or how do you know how far you are from being correct? For that, we have something called the confidence bound, or which is the basic thing that we do usually in math, where you calculate something and you check how much error can you have, how much variance can you have in your result. So the confidence region is a set of states C such that the true state lies in C with probability 1 minus alpha. Now, the problem with this is like in this many dimensions, these regions are hard to visualize. So we use simple techniques like bootstrapping or some advanced techniques like inequalities to provide error bars on this fidelity and trace distance, which ensures that our results are statistically significant and not just fluctuations. Now, we want to check how many copies can we have, do we need to actually minimize this confidence bound, that we minimize this confidence region that we have. So the scaling law, as we saw, is d squared. With respect, if we change n, the required number of n, it actually scales with respect to the d size d of the system. And we immediately have this exponential wall that we face. So if we have 1 qubit, the parameters are 3, and 10 qubits is this that we saw. So the cost of dimensionality is actually one of the things that is, this is actually the area of research that is going on right now. And so to deal with this, there are some specific techniques, something called compressed sensing, there are classical shadows, there are machine learning. I won't go deep into it, but if you have questions, you can ask me about them. And with this, we have more or less covered the full spectrum of quantum statistical inference. So this is a general summary of what we talked about. There is discrete discrimination, where we want to find the optimal measurement between a finite set of quantum states. Then which asks another question, like what if we increase the number of copies? Can we do better? Then we moved ahead from the discrete case, we checked the continuous case, where you were limit of quantum sensors using something called as the quantum Fisher information and quantum Gromov bound. Then we checked quantum state tomography, where we said, okay, we don't have just one parameter, we have the whole density matrix, and we want to reconstruct that matrix. And then we also saw how it's a very tough problem to solve. So the takeaway from this seminar was like quantum statistical inference is the mathematical framework to transform your raw experimental data into verified physical knowledge. And with that, thank you for your attention, and I'm open to questions.
Thank you very much, mate.
Yeah,
Thanks so much, Amey. That was a lovely talk.
yeah. Any questions? I mean, if no one has questions, then it was really good or really bad.
I think we might have one.
Yeah. No one?
In that case, I guess that was an amazing talk, and I think if you have any other questions, you can always reach out to me.
Yeah.
I mean, one question: do we have like access to maybe some lecture notes of this? I could expand on this if we are interested in learning more.
Yes, actually, I mean, this was, I took a course on quantum statistical inference as part of my master's program, and I can give you the notes if you want. Yeah, yeah,
Awesome, thank you.
yeah, yeah. With that, I think we can end the meeting.
Awesome.
Thank you very much, mate.